You're walking down the street, then 69. Boom! You got free tutoring. Your friend, on the other hand, 71. No mercy, no free tutoring. Welcome to the idea of regression discontinuity design, an important methodology when using observational data. Hi, my name is Bogdan Popescu, and I'm an assistant professor at John Cabot University, Rome. I also used to teach at Oxford and at Princeton. In my career, I've taught generations of students the principles of statistics and computational methods. So today we're going to learn about regression discontinuity design. So let's dive right in. Okay, so today we're discussing regression discontinuity design. So if we remember from previous lectures, there are two important methodologies for utilizing when we're dealing with observational data. One way is differences in differences, which is what we covered in the previous lecture. And another way, which is what we're going to cover today, is RDD, or Regression Discontinuity Design. So typically, regression discontinuity designs, or RDDs, utilize specific thresholds that create as if random assignment near a specific cutoff. So specifically, if we think about some individuals, there might be some subjects that are in the program if they have scores below a certain threshold, and they will be exposed to that program, and people who have above a specific score, those people will not be involved in the program. So another way to think about this is to think of the eligibility mechanism as a running or forcing variable. So there's a specific score that determines whether a person gets selected into the program or not. The second important element within RDD is the cutoff, or what the threshold is. This is really that specific number that determines whether one individual gets to participate in the program or not. It's also important to make the distinction between sharp RDs and fuzzy RDs. So sharp RDs are a methodology that refers to the idea that everybody follows the same rule. For example, if you get a score below 70, you get exposed to a tutoring program. If you get above 70, you do not. Fuzzy RD, on the other hand, reflects the idea that people don't always follow the rule perfectly. So even if you get below 70, it doesn't necessarily mean that you're going to follow the program, and the other way around. So if you get above 70, there's still a possibility that you could still join the program. So this is the concept of a fuzzy RD. So this is how we can think of how the program is reflected into the outcome. So we have a running variable, so some sort of variable that determines, for example, a score that determines whether a person gets exposed to the program or not. There's a certain cutoff. It could be either above a cutoff or below a cutoff, and those people are exposed to the program. This will result in some sort of final outcome. So the key assumption here is that potential outcomes, both y0 and y1, so the y0 from not being exposed to the program versus y1, the outcome from being exposed to the program, are continuous in the running variable at a cutoff. Of course, this is fancy jargon to essentially say that people just above and just below the threshold are very similar. Or if the program didn't exist, their average outcomes would simply change smoothly with the score, and you wouldn't see any sudden jump at the threshold otherwise. Okay, so this is how we can think of this, right? Here's an illustrative example. Let's imagine we have these 6 students. We have an entrance score. So let's imagine that we have an exam. They got certain grades. And then depending on their scores, or how many points they got on the entrance exam, there is a decision whether these students get assigned to a tutor or not. So let's imagine that we have this 70 points threshold. So if you got below 70, then you are assigned a tutor. If you get above, you are not. So then we also see the exit exam. So we see what happened after they performed in their final exam. So does being exposed to this tutoring system, does that improve the student's final grade? Okay, so once again, this is the hypothetical tutoring program to illustrate the idea of an RDD. So let's imagine that we have a bunch of students who take an entrance exam, and those who score 70 or lower get a free tutor throughout the year. Students then take an exit exam at the end, and this allows us to examine the effectiveness of this tutoring program. This is how we can think about this. So we have the entrance exam scores from 0 to 100. Here is zoomed in from 30 to 100. And we have the students who had the tutor. These are listed here in red points. And we have the students who didn't get the tutor here in black points. If you like to obtain exactly the same graph, we will have to create our own data. So this is a fake data that I created. There's 1,000 students. And then I am creating an entrance exam score following a beta distribution. Don't worry about what this means in practice. There's obviously specific parameters that you need to change in order to obtain random numbers. I encourage you to simply copy and paste this code in your RStudio file. We have also similar score for the exit exam. And then we simply create the variable that captures whether students benefit from the tutoring program or not. We also create some fuzzy entrance exam. Long story short, this is what the data generating process is, which allows us to then put that into a ggplot code. So this is the tutoring data frame that we just created. And on the x-axis, we have the entrance exam. On the y-axis, we have the tutoring text. Essentially, we have these two elements. Additionally, I'm creating a vertical line, which is this yellow line here, and I'm depicting the students with points, but I am jittering them. Otherwise, you'll probably see all these points on a single line. So this code too, you simply can copy and paste it, and you should be able to see exactly the same graph. So once again, this allows us to see what the threshold, which is 70, as we discussed. Some students didn't benefit from the tutoring program, whereas the other students did benefit from the program. This is the threshold of 70. Okay, so the assumption behind this methodology, as I already mentioned, is that students just below the threshold and above the threshold are very similar. So the idea here, from an identification point of view, is that we can measure the effect of the program just by examining the students at the threshold. So if we zoom in, so notice how this moves around, so this is much more zoomed in, we would make the assumption that these points here and these points here are very similar. The only thing that makes them different is really the exposure to this tutoring program. So this is the beauty of this methodology, because this allows us to really zoom in to that tiny, narrow bandwidth, the tiny, narrow group of people who got exposed and didn't get, or who just missed being exposed to the treatment just by a tiny margin. Then this is, for example, an interesting way to examine the effect of the tutoring program. So this is simply the entrance exam score on the x-axis, and then the exit exam score on the y-axis. So we can simply fit a linear model to illustrate the gap between the people who got exposed to a tutoring program versus not. So this is once again the beauty of this methodology, because the distance between the red line and the black line is really the causal effect, or so-called delta. This is how you obtain this graph. Very straightforward. Here I'm simply measuring the effect of the tutoring program together with the entrance exam center. This is a variable that starts with a 0 if it was exposed to the program versus not. And then I'm simply plotting it. So if you're simply copying the code, you should be able to get a graph that looks like this. Okay, so I'm writing this too. So the delta measures the gap in the outcome for people on both sides of the cut point. So here too, we can have a sharp ID that measures the local average treatment effect, the cutoff. So this is called ATE, average treatment effect. But also fuzzy RD, also labeled with delta, measures the local average effect for compliers at the cutoff. So it's important to note that there are a few internal factors pertaining to RD that can affect the size of delta, the size of this jump. So some of these include whether our estimation of delta is parametric versus not parametric, what kinds of bandwidths we're using, what kind of kernels. So I'm going to illustrate now how these different specifications could impact the size of the delta. So this was the linear model that we estimated for both the students who got the tutoring program versus not. This is an effect of minus 10.97. Students who didn't benefit from the program didn't see an increase in their final exit exam score. This is, for example, how moving from a linear model to a smooth model, we can see that this impacts the size of the calculated delta. So from minus 10.97, we get to minus 9.16. So this clearly affects the estimated effect. The same thing if we go with a potential cubic model, we see that now the difference is even bigger, minus 11. So I hope this clearly demonstrates that the type of line that we're trying to fit is going to impact the size of delta. So one common way is the locally estimated scatter plot smoothing, which is what you saw here, but obviously this is also another type of smoothing. So the gap fundamentally can be measured by centering the running variable around the threshold. I guess one of the questions would be, what does centering the running variable around the threshold mean? So this essentially means that we're redefining the variable such that the cutoff equals to 0. So this is, for example, how we can think about it. So we have all these students who got an entrance exam. This is their exit exam score. And then essentially this is what we're trying to estimate. So we're having a running variable, which is centered. So what score did they got on their entrance exam, and then we have the treatment, whether people got exposed to this tutoring program or not. Okay, so this is how we estimate this effect. So this is a pretty table that can be interpreted in a very straightforward way. So here's the program data. I'm creating the centered variable. So as I mentioned, I'm subtracting minus 70, so to center it around 0. And then I'm estimating this effect. So you have an exit exam. So this is what my main outcome is. And I'm interested in the effect of the entrance exam centered and the tutoring program. And then I'm simply plotting the effect on here. Okay. So this is the table that I obtained. So this is the interpretation. So the entrance exam, we simply say that for each 1 point increase in entrance score, the exit exam increases by 0.514 points, holding the tutoring status constant. Similarly, for the tutoring status, we say that students without tutoring score, on average, score 10.97 points lower on the exit exam, holding the entrance score constant. So essentially, we're learning that the tutoring program, in fact, works. So this was how we depict this effect, as I showed you earlier, how we depict this when we're using linear models. So the estimate, the precise estimate, can also come from this package, which is called RD robust. So to obtain the exact effect, we would do something like this. So first of all, we would need to install the package called RD robust, and then we would do something like this: RD robust we are defining our y, so this is the exit exam, so what score people got on their final exam, and then the x is the entrance exam. And we specify our threshold, which in this case, as we've argued so far, is 70. And then finally, we want to extract conventional coefficients. So this is also a smooth line that tries to indicate the difference between being in the program versus not being in the program, minus 999. So one important parameter that's also going to affect the gap, the size of the gap, is also the bandwidth. Essentially, how close are we getting to the cutoff, right? So if we're getting really close or we're staying far away from the cutoff, that will also impact the results that we're getting. The important thing to note is that, as you might remember, or as you might imagine, the observations that are too far away from the cutoff shouldn't matter because those observations are way too different from the results from the cutoff, like from the individuals that just barely got into the program versus not. So that's why they're not really comparable. So to think about our specific example, imagine having to compare people who got really bad scores on their entrance exams to people who got very good scores on their entrance exams. So of course, they're not really comparable. So that is why it is advisable to focus on individuals very close to the cut. So here's, for example, what happens if we focus on the 5-point bandwidth. So I highlighted just the ones that are within a 5-point bandwidth. So notice here minus 10.17. This is what happens if I focus on minus 10. On a 10-point bandwidth. So notice here that our gap shrank, like from minus 10 to minus 9. So this is clearly, hopefully, an indication that bandwidth size really affects the size of the gap. Of course, a legitimate question here would be, what do we choose? So in order to decide what the optimal bandwidth is, we should use again the RD robust package. So in order to extract the optimal bandwidth, we would simply do something like this. RD out $BWS. So this is the optimal bandwidth for the conventional estimate. So that gives us this bandwidth, 7.6. So if we use that, we would be getting this effect. So here, what we see in this graph is exactly the bandwidth of 7.62 and an effect of minus 9.72. Again, all of these graphs clearly suggest that the tutoring program is effective at getting people better scores in the final exams. Okay, in principle, just to give you some suggestion for practice, it's always a good idea to present multiple bandwidths to show that the results are not sensitive to the selection of bandwidth. And it's also a good idea to select, on the one hand, the ones that the bandwidth that's recommended by RD Robust, but also some other bandwidths that make sense. Okay, the other important element that's going to affect the size of the gap is the choice of kernel. So what is a kernel? Kernel can be defined as the method for assigning importance to observations based on how far off they are from the cutoff. So here we could have a uniform kernel that would look more or less like this. So this essentially is just a specific parameter when we run RD robust. So this is, for example, what a uniform kernel would look like. So this is, if we use a uniform kernel, we would get minus 10.93. If we use a triangular kernel, we get minus 10.64. If we use an Epinechnikov kernel, we would get minus 10.78. Of course, these changes seem to be minimal, but once again, the kernel is impacting the importance that's given to different observations. So to replicate these graphs, you simply copy and paste these codes. This is going to allow you to obtain a graph very similar to mine. Of course, the code for ggplot is a bit more complicated because I wanted to really depict both the kernel, but also or we wanted to weight the observations. But hopefully, if you simply copy and paste this code, you should be able to obtain a graph that looks like this. Okay, so in the end, there's so many moving parts, right? I mentioned bandwidth, I mentioned kernels, the order. So in the end, which ones do we choose? So my recommendation is to use RD Robust and present all the results. So to have something that looks like this. So you have here the type of kernel in place, right? So this would be uniform kernel, triangular kernel, epanechnical kernel. Then you have conventional RD, you have bias corrected RD, and you have robust bias corrected RD. So ideally, you want to present all of them. You can also see here that you have bandwidth that's specified. So in this iteration is 5.64, in this iteration is 10.607, and the same in the robust biased corrected version. Once again, if you simply copy and paste this code, you should be able to obtain exactly this table. So this is a good way to demonstrate robustness, to show how the results that you're getting could change as a result of kernel, as a result of the bandwidth, and so on and so forth. So feel free to play around with the code and see if you can get exactly this table. Okay, so a reminder, the gap, the cutoff, this thing that kind of changes depending on the parameters that we're selecting, is called local average treatment effect, or late, right? The findings have high internal validity, meaning it clearly reflects what's happening really at that cutoff, but have low external validity. So this means that the findings are limited in scope. So the reason why I'm mentioning this is that in every empirical paper, the authors should reflect on to what extent their findings could apply to other contexts or outside the very tiny analysis. So one additional credible step in order to ensure that the RD results are robust is to use falsification tests or placebo tests. So placebo tests fundamentally in this context examines discontinuities at points where no treatment should occur. So having these kinds of placebo tests ensures that the observed treatment is not, the cutoff is not an artifact for underlying trends or some model misspecification, and there are also no jumps at other types of thresholds. The way to do this is to run RD at different values of the running variable. So in our case, it would be 60, 65, 75, 80. Remember that in our case, the threshold was 70. So we want to make sure that the delta, so the gap at all those different points, is zero, those other gaps. So here's, for example, an illustration of this. So remember that our threshold was 70. So clearly, the people who are not benefiting from the tutoring program seem to be doing worse in their final exam. And then if we take to 75 as a threshold or 80, we do not see any result. So the reason for why I'm saying this is because we have these confidence intervals that overlap with zero. Okay. This means that also pre-treatment covariates should be balanced across the threshold. So the reason why it's important to have pre-treatment covariates, this allows us to evaluate this continuity assumption that pertains to RD design, but also further reinforces our belief that we do not have selection bias. So this means that we can interpret the delta causally. So when I say covariate balance in this specific example, we could test for covariate balance when it comes to age, when it comes to income, when it comes to maybe a race of the student. These are all three different variables for which we may want to do covariate balance prior to running the RD. What's happening if we run the RD on these pre-treatment covariates as outcomes and there is no jump? This means that the assumption of continuity holds. Okay, the one caveat that's important to mention is manipulation at the threshold. So what does this mean? This means that people might be aware of the program and they might manipulate the threshold so that they can become part of the program or not. For example, students could try to get a slightly lower grade just to get into the tutoring program. So this means that people at the cutoff are no longer representative of the treatment and the control group. One way to check for this manipulation is to run what is called the McCrary Test. This McCrary Test is specifically designed to investigate manipulation just around the threshold. What I'm doing here, rerunning the data set, I'm recreating it. A McCrary test can be simply calculated using, so if you cannot really see it here, I cannot scroll further down, but if you copy and paste this code on your machine, you should be able to see the code that I use. So the McCrary test tells us essentially that there's no difference between students who just got, who didn't get to benefit from the tutoring program versus the students who did get to benefit from the tutoring program. The question is, what would it look like if we had manipulation? This is an example of manipulation. Hopefully it's vivid or the difference is very clear. Here we do have some indication of manipulation. So it seems to be the case that people who just got at least in this hypothetical example, people who got above 70, they were close to this threshold, they got lower grades in order to benefit from the program. So the caveat 2 has to do with non-compliance. So what does this mean? It means that people at the margin might end up both in or might end up outside of the program. So this is an example of this. So these are people who originally should have benefited from the tutoring program, but there's a bunch who decided not to do the tutoring program. The same here. There's some people who shouldn't have had a tutor, but for some reason, a few exceptions, a few students decided to do the program with the tutor. So this is compliance and this is non-compliance. Hopefully this is very clear. So the way to address non-compliance is by using fuzzy RD. So fuzzy discontinuities fundamentally use an instrument for each side of the cutoff that people should be on. So then the effect will only be for compliers just near the cutoff. So here's how we can think about compliance. So imagine that we have 4 person types, and then we have 2 columns if people are assigned to treatment and if people are assigned to control. So a complier is someone who takes the treatment if they're assigned to treatment, and a complier is somebody who doesn't take the treatment and is assigned to the control group. An OS taker is a person who always takes the treatment if they're assigned to the treatment, and then that still takes the treatment that they're assigned to the control group. This is an interesting juxtaposition of taking the treatment or whether they pertain to the treatment versus the control group. A never taker, even if they're assigned to the treatment group, they never take the treatment. Even if they're assigned to the control group, they never take the treatment. And finally, we have a defier. A defier does not take the treatment, even if they're assigned to the treatment, and takes the treatment if they're assigned to control. So this is what the situation would look like in our case. The red figures represent students who got the tutoring program. The black ones are the ones who didn't. So the squares are the always takers. Once again, always takers are people who take the treatment if assigned to treatment, and they also take the treatment if they're assigned to control. So here they are. Compliers are these ones and these ones. So compliers are these people. They take the treatment if they're assigned to treatment and do not take the treatment if they're assigned to control. Finally, you have never takers. These are the triangles. So let's look at the definition. Never takers are people who do not take the treatment if they're assigned to treatment, and does not take the treatment when they're assigned to control. So hopefully this illustrates this idea of compliance. One question you guys may have is this idea, why don't we include defiers? So we don't include defiers because these would be students who do the exact opposite of the rule, right? So they refuse tutoring when they're offered, and they will take it when they're not. Of course, in real life, we assume that people don't usually behave this way. Okay, so how do we address non-compliance? We can use an instrument, so just above and just below the threshold to address non-compliance. And this instrument has to meet three important criteria. So the first one is relevance. So what does this mean in practice? Relevance means that the cutoff changes the likelihood of getting the treatment. So people below the cutoff are much more likely to get tutoring. The second important criteria is exclusion. The cutoff affects the outcome only through the treatment, right? So crossing the threshold doesn't directly change the outcome except by changing whether the student gets the tutoring program or not. And finally, the third important criterion is exogeneity. So what does this mean? This means that there are no unobserved confounders between the tutoring program and the exit exam that are unrelated to the cutoff that could be impacting students' performance. So how do we address it? So here, once again, the original exam score affects whether, so the people get some scores and then they're below a cutoff, they receive treatment and that affects their outcomes. So this is how we do a fuzzy RD. So we have the exit exam as a Y parameter, we have the entrance exam as the X parameter, and then we have a fuzzy tutoring parameter, right? So this is what we get when we run this command. This is also how we can estimate it and present both first stage and second stage. So to obtain this, assuming a uniform kernel, we would simply do this, RD robust. We explain here the fuzzy component of the program, and then we save all these models. So feel free to copy and paste all this code in order for you to obtain a similar table. And then this was uniform kernel. This is triangular kernel. Notice, for example, how the estimate changes. So when we have uniform, it was 18. When we have triangular, we have 16. And when we have Epinechnikov, we have 17. I'm looking at all these results here. Okay. So this was it in terms of regression discontinuity design. So the goal of an RD is to estimate local causal effect of the treatment at specific cutoffs using a continuous running variable. So the key assumptions behind an RD is the fact that there is continuity. The outcome Y0 and Y1 change smoothly at the cutoff. There's also another assumption is that there's no precise manipulation. So units cannot decide or they cannot sort themselves out into the treatment versus not. We also discussed specific diagnostics pertaining to RD. So those include McCrary tests. Those are specific tests for threshold manipulation, covariate balance. So it's important to have no jumps in the pre-treatment, and then placebo tests. We can just move the cutoff arbitrarily to see if we have jumps at other thresholds. So when we get the RD results, we're fundamentally getting local average treatment effects or late at the cutoff. It's also important to note that RDs have very good internal validity, but they have very low external validity. So researchers always have to wonder or always have to reflect on the extent to which their findings applies to other samples. Thank you. I hope you enjoyed this video. If you found it useful, please don't forget to subscribe, give this video a thumbs up, and please comment down below if there's something in particular in relation to R or to ggplot that you'd like me to make a video about. Thank you and see you soon.